Hello, Sarah. Hello. And hello, everybody. Hello, Miriam. And right when hello, Sumaya. Good afternoon. And hi, Montserrat. And okay, and right when you guys came on, my board dropped out. Hello, Osmael. Good afternoon, Stephen from 2D. Okay. And sorry, and speaking of 2D, it was like 1D because right when you guys came on, my board. Hello, Brian. I don't know what, it's not cause effect. I don't know why my board keeps failing on me. It's so, whoa, hold on. Top of the afternoon, Abdel, top of the, there. What is going on? Not with Abdel, with, no. Okay, and there are people in the waiting room, I know, I see. Okay. Okay. Okay, my board is back, it's good, and it's someone, and okay. 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 Okay, so one thing before so we're going to do new material or continue the new material right now. One thing is I apologize. I really apologize. I do not have your exams completed yet. I do not have them graded. I do not have them to return. I was really hoping for today. I was trying for today. I failed. Obviously I will get them back as soon as I can. I don't know if it'll be this Wednesday because now that I didn't succeed for today. Good afternoon, Jeff. More people coming. Hold on. I really do. Oh, and my board just stopped again. Why does that keep happening? Hold on. But no, I truly sorry that I do not. I'm just going to repeat just to be clear. I'm not happy about it. I'm not proud of it. And it's totally my fault. I not have your exams. Wait, and there's someone in the waiting room. And my board keeps falling off. Okay. I will have them as quickly as possible. I don't know if that will be this Wednesday, to be honest, because Tuesday is my big travel day, or today it's Tuesday. I don't get a lot done. But I will try. If I don't have them back Wednesday, then it's not like I'm going to wait until the next class. I'm just going to keep grading them, and so you'll get them in Google Classroom when you get them. Sorry. The couple of concessions, in fact, I'm going to just put this in the chat. Hold on a second. So again, I'm just saying, I'm not happy about this, but I'm just saying to be clear, and it does not mean the grades are bad or anything like that. And I know it causes anxiety not to get the grades back. You will get them as quickly as I can get them to you. There will probably be some kind of extra credit opportunity or something to put back a few points on the exam if you need it. I'm not saying you necessarily do. Oh, the board, sorry, the board. This drives me crazy. No, it doesn't. I'm already crazy. I know. But why does this keep happening? While the board is making up its mind, I'm going to put in the chat a couple of things. I'm just going to, all right, hold a second. Someone else is here. Right, sorry. If by the way, if someone joins right now, do they see what's in the chat that I'm writing, or will they only see what's in the chat that comes after they join? Do you know? Can anybody tell me? Like, I'm putting things in the chat for everybody, but if someone just comes on right now, will they see what I'm putting in the chat? Like, oh, hello, just to say, you do. Yeah, but okay, you see it. But I mean, if you were to join right now, would you see it? Well, okay, almost.
No, you don't.
Okay, all right. So then, okay. Thank you. So let me see if I can. Okay, you don't think so? All right, so hold on. I'm just doing this again, just partly because my board is not working. Some of this is on my board. I mean, my board will work again in a second, I hope. But oh, you just joined, you did not see it. Okay, thank you. I appreciate the honesty and thank you for joining. So I'm putting it in, I'm recopying it right now. And I'm just saying this as many times as possible, not to dwell on it. And some of you, I mean, I'm not assuming that everybody, but I know that it upsets some of you not to get things back, and it should. Like, I mean, I know it makes some of you nervous not to know, like your grades all the time. I totally respect that. I apologize. So I'm just making it as clear as I can. And oh, good. Okay, thank you, direct chat person. I see that. Thank you. Okay, so but now what I'm putting in for everybody, some of you, this is a repeat. I just want to make this information clear. And to some of you, this is all old information. But you know, some of you contact me a lot, and some of you don't, and that's totally fine. Some people say, if you're like me, you're the kind of person that would like never contact the professor until there was an exam, and then I'd be like freaked out or whatever, and then I might reach out. So I totally understand that. So in case you never knew, you know, please, if you have any, if you're just like worried or something, even before you get your exam back, you can text me at that number, or email me. Also, one last reminder, we're going to go on with new material in a second. I'm just trying to establish this because I know it stinks not to. I know you're waiting for your exams. Oh my God, and I'm waiting for my board to work. So this is just what I can do in the meantime. Also, and there goes my board again. Okay, just to be clear, so tomorrow, some of you now, I think this came up last time. And by the way, you were all very, very sweet last week. I mean, believe me, it was very touching. I got a bunch of texts and stuff from you guys afterwards. I know that was all very awkward, whatever. But it was very sweet, all the sentiments I got from you after class last time. I totally remembered. All the more reason I wish I had your exams for you. Although maybe in some cases it's a good reason not to give you exams. But anyway, so some of you know where I live on the 4th floor, but I'm putting it here in the chat. On the 4th floor, like you come out of the elevators, the South Bank elevators, like the men's bathroom side elevators. You don't go into any of the back rooms where any of the regular labs are. You just come out of the elevators and head right as though you're going to the jaywalk. Like you just walk toward that window that overlooks the jaywalk on the 4th floor. And there's one strange door right before the window to the jaywalk that you would never have any reason to notice unless you were looking for it. And it's there, but it has my name. That's me. It has my name on it. The door is often closed because it slams shut automatically, but there's a doorbell that works. So I'll be there on and off. I'm not saying I'm free every single minute. I do have on and off meetings like all day, but I will be there from 11 a.m. to later than you, like till like 6 p.m. or something like that. On and off, on and off. So please feel free. Again, I'm not telling you to, but if you're concerned about anything or anything like that, and I'm not pretending that that means I'll have your exam graded by tomorrow. I'm not saying that, but I'm just saying if you're worried or you want to check in or anything that And the door's to the right. Yes, there you go. Yeah, the door to the right. Exactly. So there you go. So again, I will be in meetings on and off and Zoom meetings, stuff, but I'll be there. And you can come in, and even if I say, could you come back in 20 minutes or whatever, or you can just say hi. So often I rush anyway. But again, I apologize. I'm doing the board thing again, but that's the deal. And the only other thing I can say is, yes, there's a game turn assignment posted for tonight as usual, which many of you know at this point takes 2 seconds to do. But I'm not assigning any new problems or anything like that until we get out from under this exam. So you can at least breathe a little bit, maybe. Okay, the board is hopefully coming back. Here we go. Okay, so that said, so there's my last apology for the moment. But then they're just going to come when they come. Like, I'm not guaranteeing that they're going to happen on Wednesday, because now the next 2 days are complicated, but they'll be in your Google when they are. They might come one at a time. But until then, we just have to go on with new material. So again, if there's any issues or complaint or concerns, put in the chat directly, or text me or email. But other than that, I'm going to go on with new lecture material, some of which you already got introduced to in the lab, which I know is often it's confusing to see things first in the lab and not know what the theory is behind them. And then for other people or other times, it's confusing to see something in a lecture and not have anything to picture or apply it to or practice with, like in the lab. Either way, starting things in lecture and then later seeing them in lab can be confusing and frustrating. Starting things in lab and then seeing them in lecture can be confusing and frustrating. Just like, by the way, seeing things in calculus class but not having any application for them or any context for them can be confusing or boring or alienating or something. Whereas seeing things in physics class before you ever felt like you learned it in a calculus class can equally. The truth of the matter about education is it's all just cycle. There's no perfect point to begin anything. The way to learn anything is to just keep cycling through it and running around the mulberry bush and practicing it, honestly. So that's all to say, which is also why, by the way, if any of you ends up for whatever reason taking this course again, because there's always a few people that do, there is no shame in that. I'll just tell you right now. I mean, there might even be people in the room. No, I don't think any of you are those people. But if you ever end up having to take a science course again, i.e. you get an F the first time, please know there's no shame in that. And many of us, and it just means you're going to see it a second time and you'll do much better the second time. And if it happens to be with me, if you ever see me twice in the same course, not only do I treat you with a blank slate and a fresh slate the second time, but more than that, I'm like compassionate and sympathetic and know what you might be feeling because I've been there. So I just consider it all the more my responsibility to make sure it really works out for you with you the second time. So, I mean, I'm not saying that that's happening to anybody here, but everything is in education is like go around until it sinks in. So that said, I want to go back to the Newton's laws stuff that I introduced in lecture. That I introduced in lecture last Monday. Yeah, I introduced 3 laws that you've seen before somewhere in your life in lecture on Monday. Newton's first law of motion, Newton's second law of motion, Newton's third law of motion. Newton's second law of motion, down here at the lower left-hand corner of this screen, sum of the F's equal ma, sum of the forces equal mass times acceleration, or net force equals mass times acceleration. That law is the most mathematically productive of the 3 laws. It generates the most quantitative information. That's the one that sort of the rest of physics ends up being very, very reliant on. That's where most of the rest of our activity lives, is in Newton's second law of motion. That's what some of your lab activity, I think, recently has had to do with. What I want to do today is start formally showing you how to do diagrams that are crucial for the application of that law. Again, you may have sort of already been doing this in lab, but you might feel like you don't know what you're doing or where. It just may have come out of left field. So I'm going to back up and try to explain how to do these diagrams and why we do them. So let me go so the kind of diagrams we're going to do today, well, this week, are called SSs and FBDs. That's what my illegible handwriting up there says, SSs and FBDs. SSs, so number one, SS. What we're really going to focus on today is an SS. That stands for system schema. We're going to do system schemas today, which is one type of force diagram. And then we use system schemas to generate or to allow ourselves to make another kind of diagram called an FBD, a free body diagram. Okay, we won't get to those today, probably. Again, you've probably already been sort of doing it in lab, but you may or may not feel like you know what you're doing. And I think free body diagrams are a lot easier to make if you have a system schema from which to make the free body diagram. So we do, in lecture, we do system schemas first, then we're going to do free body diagrams. And free body diagrams, there's two types, really. There's something called a pure free body diagram, so it says 2A there on the screen. And then there's something called a component or a vector component free body diagram. So the real idea here is that we make a system schema, which allows us then to make a pure free body diagram. A pure free body diagram allows us or enables us to make a vector component free body diagram. And the point of the vector component free body diagram, the ultimate point, which we'll complete on Wednesday of this week, the ultimate point of that is to show you what all the magnitudes, and you may want to write this down, it doesn't say this on the sheet here, but here's the context of this whole thing. The purpose of this sequence of diagrams is that by the time you get to the third diagram, the component diagram, the arrows that you find in the vector component free body diagram show you the magnitudes and the directions of all the forces that you're going to identify, write down, expand, and quantify to plug into the left side of Newton's second law of motion. In other words, down here at the left lower corner of the screen, like where it says net F equals MA, or it says sum of the F's equals MA. The whole concept of all of this is that all of the beginning of this semester, we were really studying the distinction between velocity and acceleration. The whole idea is that if you just leave an object alone, it will have some velocity that you might call 0, or you might call some other number. And you might call going to the north at 30 degrees, or you might call going to the southeast at 40 degrees, all depending on who you are. That is, every single object has a velocity whose magnitude and direction totally depends on who's or what's observing it, right? The whole first part of this semester is saying velocity is a relation between two objects. What your particular velocity is not a matter of objective reality or a matter of your intrinsic properties. What your actual velocity is totally a comparison to some other object that might be observing you. What objects do when they're left alone is not necessarily sit still or necessarily move at some particular speed. What objects do when they're left alone is they maintain constant velocity. In order for them to change their velocity, i.e., in order for an object to accelerate, what we're now saying is it needs to be influenced by a second object. Okay, so an object left alone maintains a constant velocity. In order for it to accelerate, it must be influenced by forces coming from other objects. It turns out that Newton's laws then get us into, okay, when second and third and fourth objects interact with a first object, when they push it or pull it by means of these interactions that we call forces, all those other objects will accelerate, will change the motion of a first object. So all of Newton's laws are about, well, and particularly Newton's second law is saying, if you actually know the magnitudes and directions of all the forces acting on one object at a point in space, at a point in time, then you will know the acceleration, the change in velocity of that object at that point in space, at that point in time. We don't need forces to move. We just move automatically. We don't need forces to have velocity. Velocity is in the eye of the beholder. You have a velocity automatically depending on what the object looking at you has. But in order to change your velocity, in order to speed up or slow down or turn, you need to be forced. Any individual object, in order for it to accelerate, needs to be forced into acceleration by some other objects. So Newton's second law says the sum of all the forces acting on a mass will produce the acceleration of that mass, okay? And it's a quantitative mathematical law. The sum of the forces along any particular axis of space will, divided by the mass in that axis of space, will yield, will produce, will calculate, will predict the acceleration of that mass along that axis of space. So sum of the F's equals ma. The whole challenge of physics, it's a simple, straightforward equation. Plug in all the F's, divide by m, you get the A. The challenge of the computation is not generally what bothers anybody, any physics student or any physicist. The challenge to physicists and physics students is what F's, how do we know what to plug in to the left side? How do we know what the magnitudes and the directions are of the given forces? How do we even know what are the forces to even list to put into the left side of Newton's second law? The way to know what to put into the left side of Newton's second law is to draw these diagrams that I'm now going to show you. Okay, so this is the larger context. The context is once you know all the forces acting on an object, you divide by its mass, then you know the acceleration of that object. And once you know the acceleration, then it goes back to all the equations and all the practices and all the principles we learned in the first part of the semester. Once we know the acceleration of an object, then we have all these equations and relations that enable us to predict where the object will be at a certain given moment in time, or where the object was at a certain given moment in time, or how much time it will take the object to reach a certain place, or how much time it did take the object to come from a certain place. Whether we're predicting the future or solving crimes, the whole idea is if we know the A, we're good to go. We can get the V, we can get the X of any object in time and space. But in order to get the A, the Newtonian program now is, in order to get the A, in order to solve for acceleration and then plug into all our old equations, we need to know the F's. F net equals ma. How do we know and quantify the F's? We draw diagrams. So that's what we're about to do. We're about to learn how to draw diagrams in order to figure out what F's to put in to F net equals ma, in order to get A, to go back to the physics that we just got tested on. So the first kind of diagram we draw is called the system schema. That's what I'm going to show you right now. Okay, so here and again, stop me at any time in any space. And again, thank you for last week. It was really touching. I'm not forgetting, and I'm not losing my mind because it's already lost. All right, so we're going to turn this. So, okay, so system schemas. Here we go. System schemas. Pictures for identifying forces acting on an object. Oh, and right, there's that. Just to be clear for anybody who just joined in, I'm sorry. I'm sorry again. I'm sorry. Okay, next page. Okay, I'm not making a joke about it. I am. Okay, so here, so this page is just saying what I just said, but just to put it in focus, we're going to make a series of 3 diagrams in succession. Each one comes from the last one. Like we need the first to make the second. We need the second to make the third. And we're going to need that third diagram in order to identify and expand the net force, the left side of F net equals ma. And by the way, notice that sum means sum of all the forces. So the whole key behind this law is that all the forces together produce the acceleration of an object. So in order to get the acceleration, we need all the forces. And how to know what is a force or what's not is where the pictures come into play, okay? Notice every time I write that law, like sum of the F, I always write an arrow over the F and I write an arrow over the A, trying to emphasize that this is a vector equation, that just like acceleration is a vector quantity that entails magnitude and direction. Same thing with force. A force is something that is a quantity, is a measurement that has magnitude and direction. And so every time I write F net equals MA as a vector equation like that, what I'm really secretly saying, we said this Monday, hopefully you have this in your notes, but make a mental note. Every time I write some of the F arrows equals MA arrow, I'm really saying that simultaneously yet independently, there are really three equations occurring. I'm saying the sum of all of the horizontal forces on an object makes the horizontal acceleration of that object. The sum of all the vertical forces on an object produces the vertical acceleration of that object, and the sum of all of the transverse forces on an object makes the transverse or whatever acceleration of that. So it's a vector equation. It's really three simultaneous yet independent spatial equations in one. Okay, so that's our goal. Again, I've just repeated it like 50 times. All right, so now in order to draw a system schema, we're going to use first the simplest example I could think of, which is an example where there's only one force operating. Let's think of the example of free fall, where something is free falling toward the center of Earth, toward the surface of Earth, something like a tennis ball or a brick or whatever. And remember, the definition of free fall means only one force acting, only the force exerted by the center of Earth on all nearby objects, that force that we generally call gravity. Let's assume that's the only force acting on an object. Let's talk about how we would draw the system schema for this one force situation, and then we'll do one for a two force situation and then a three force situation so that you see how system schemas work. And again, system schemas is as far as we're going to get today. We'll do free body diagrams, both kinds, on Wednesday. Okay, so we're going to draw a system schema in the context of free fall. Okay, free fall. So system schema. All right. So first of all, instruction A. This is how to draw system schemas in general. A, in a system schema, we represent our mass, the mass that we're talking about, the mass, the M in F net equals MA, the mass that we're looking at, whose acceleration we ultimately want to predict, our object of concern. We're going to represent that by a dotted circle. And then, online, if you look these things up, there's some subtle differences in different web pages and stuff like that, and that's fine, but this is my standard. So we take our mass and we're going to represent it by a dotted circle. I'm going to do that in a moment. I'm just giving you all the instructions first. So then we draw one solid circle somewhere, anywhere nearby on the page, one solid circle to represent each mass in the world that's interacting with our mass of concern. Okay, that's what the handwriting said. So I'm saying in general with system schemas, first you draw a dotted circle to represent your object. And then for every object in the world that you believe is exerting a force on your object, every actual identifiable concrete material object in the world that you believe to be interacting with your object, you're going to draw a solid circle for each one of those objects. Now, how are you going to know? How are you going to know what objects are interacting with your objects or not? Well, that's the challenge. That's the art of the science in a way, but I'm going to give you hard and fast rules for that. That as long as you follow them, you won't have any problem. They're a little bit tricky, but they are hard and fast rules. The summary of those rules ultimately is to know what objects are interacting with a given mass. The answer actually always is going to be the center of Earth, because it always is, because Earth is always pulling on everything gravitationally, okay? So if you want to write this down or if you want to make a note of this, in every system schema, the objects that you're going to draw nearby your dotted circle are going to be the center of Earth. It's always going to be there in every single scenario. And then you're going to draw every single object, all and any objects that are in any way touching your object. It's actually that simple. I'm going to be expanding this idea for like the next, 40 minutes. But actually, the deal is in every single system schema, in every situation, no matter how complicated, planet Earth is always there. or the center of Earth, is always there pulling gravitationally. And then every single other object that's touching, literally, like in physical contact with our object of concern, will get depicted, and nothing else, only those. So it's gravity plus all the touches. Like, that's actually the deal. I'm going to expand on that now, but so for every object in the world that's either is planet Earth or something that's touching our object, we're going to draw a solid circle. Again, you'll see in a moment, but that's what we're going to do. All right. Then what we're going to do is between each solid circle and our dotted circle, we're going to draw a solid line. Okay. The solid lines that we're going to draw, those ultimately represent the forces. The reason for this whole diagram, remember, is to have a clear and confident list, ultimately, of what all forces are acting on our object. What we're ultimately going to find is that every single line that's in our system schema is a force, that ultimately we'll get a number and go into the math that we're going to do. But the way to know what goes into the math is going to be every line that's in our system schema will be a force. Now, the way we get the lines, and this is the purpose of the system schema, the way to know how to draw lines or what forces to bring in is to know that a force is an interaction between two objects. So if I am a mass, no force can ever act on me unless it's coming from some other object. That's really the principle behind this whole thing. In other words, this is the non-Star Wars part in a way. The non-Star Wars part is that forces don't just exist. Objects don't just have forces, and forces don't just come from the sky. A force is an interaction of another object on me. In fact, remember Newton's third law. Newton's third law is if I push you, you push me back with exactly the same magnitude and in the opposite direction. A force is a mutual push or pull between two objects. You cannot have a force without having two objects that are then interacting with each other. And there's two ways that objects ever interact with each other. Well, pushes and pulls. But another way to say it is there's two ways that objects ever interact with each other. Either because they're gravitationally attracted, i.e. planet Earth and something, or they're touching. It's like literally that simple. So again, I'm going to show you a drawing, of course, in a minute. I know this is all a little bit abstract right now, but what I'm trying to drive home right now is, in order to know what forces are acting and what force and what are not, like in order to know what are the forces acting on an object, which again, let me tell you, that's the hard part of physics or of this part of physics. Like the people always say, I can do physics, but I don't know how to start any given problems. The thing that people have difficulty starting with, like force problems and F net equals ma problems and Newton's law problems, they always have difficulty knowing what's a force and what's not, or what are the forces acting on a given object. The way to know is you cannot say that a force is acting unless you can name an object. You cannot say a force is acting on a mass unless you can name some other mass, some other object that is pulling or pushing on your first mass. So in drawing these system schema, we draw a dotted circle that is our mass. We draw a solid circle for anything and everything in the world that's interacting with it, which means planet Earth and anything and everything that's touching it. We draw a solid circle for each of those things. And then we're going to draw a line from the solid circle. From each solid circle, we're going to draw a line to our dotted circle. And each line ends up representing a force. And it'll have a name and it'll have a number and stuff like that. Okay, now, weird last point, very weird point, very super important, kind of tricky point that I'm going to make here, that again, I'm going to show you in the pictures. I'm going to spend the rest of this period showing you in pictures what I'm saying here. But this last line says that every one of your connecting lines, every one of the lines that you find in a picture, excuse me, in a system schema picture, every line that you find will ultimately be a force, to go in to our equations. Okay, that's why they're important. But every single line you find is going to follow the one touch, one line rule, with two exceptions. Just bear this in mind. I will show you. But there's this rule, one touch, one line. For every touch, for every two objects that are touching, there'll be a line. For every line that you see, that represents two objects touching. But there's two exceptions to that rule. There's not a million exceptions. there's not one exception, there's exactly two exceptions. And the two exceptions are almost as important as the rule itself. Like the exceptions come up almost as frequently, if not as the rule. And they sort of make the package that is the point of this rule. The two exceptions to the one touch, one line rule, let me just add something here. The two exceptions are the pull of gravity from the center of Earth, which we ultimately call weight. So how the amount that any object is pulled by the center of the Earth, gravitationally, we call that the weight of an object, you'll see. That's an exception, always an exception to this one touch, one line rule. Hold on a second. And when I say it's an exception, you're going to see what I mean. Oops, sorry. Sorry. The pull of gravity is an exception in that in every single system schema that you ever draw, there will be planet Earth and there a solid circle for planet Earth, and there will be a line representing the pull of gravity from center of Earth. But that line that you'll draw, and it'll be in every single one. So it's super important. But it's an exception. You have to draw it first because it's going to be the one line that you'll see in your whole picture that does not represent a touch. This is why gravity is exceptional. Gravity is really weird. Gravity is one force, the only force in mechanical physics, in Newtonian physics. Gravity is the only force, the only pull that exists between two objects that somehow doesn't involve the two objects touching each other. It's so every other force that we ever identify will identify by noticing that two objects are touching each other. When Earth pulls something gravitationally, it doesn't touch. That is actually so weird and so exceptional that I wouldn't even believe it. Like, I don't even know how gravity can do that. And I certainly don't expect you at this. I'm not saying that we assume that we understand it at this point, but we just see it all the time. Gravity is so weird that we wouldn't believe in it at all. We wouldn't even put it in diagrams, except that it seems to be always there. So there's, first of all, always a line in every diagram that represents the pull of gravity, and it's the one line that's in every diagram but does not represent a touch. Every other force that you're going to draw in a system schema represents a touch. The other exception, though, you'll see in 5 minutes, is whenever you have not two objects being pulled gravitationally, but when you have two surfaces pushing against each other, which is frequently. I mean, it comes up a lot, but if you have two rough surfaces, two realistic rough surfaces pushing against each other, well, they'll touch, all right. But they're also an exception to this rule because in their case, when two surfaces touch each other, you're going to see that we're going to draw two lines instead of one, okay? So gravity is one line with no touches at all, and surfaces pushing on each other is a touch that gets two lines. Other than that, everything in our diagram, if there's a touch, it will get a line. And if we see a line, it means there's a touch. And that's it. This is how we draw the diagram. So you draw planet Earth, you look for any surfaces that are pushing each other, and you deal with those two things. And then other than that, you look for anything and everything that's touching your object. And if it's touching it, then that's going to be a solid circle with a line connected to your object. And that's how it goes. And then the purpose, and then at the end, you're going to count up all the lines that you see and say, okay, each one of those lines is a force that I'm now going to turn into an arrow and put into my free body diagram. And then I'm going to do something with that. And then I'm going to do math with that. Okay, so it's a process. But now, this has all been very abstract. I know it's all meant to be abstract rules that help you make concrete pictures out of invisible things called forces. So here we go. Let's apply all these rules to the example of free fall. I'm going to do 3 examples, and then we're going to be done today. I'm going to do 3 examples of system schemas so I could show you each one of these sort of rules in action. The first example is a free falling mass, like a free falling mass of mass m. Okay. And remember, free fall means that it's just being pulled toward the center of the Earth. It might be moving up. It might be moving to the side. Like it might be a projectile, like from your exam. But the only thing pulling on it In other words, nothing is touching this object at all. It's just being pulled gravitationally to the center of the earth, and I want to diagram it. Okay. And we know that if something is falling to the center of the earth, then it's falling at a constant rate of acceleration that we generally designate with lowercase g, like 9.8 meters per second squared, or 9.81 meters per second squared, or 10 meters per second squared, or 32 feet per second squared, or if you're on the moon, 1.16 meters per second squared, whatever it is, we call it lowercase g. So here we go. The diagram is right there. I guess I've already drawn it, which is a little unfortunate, but here's a diagram. Notice first, I drew a dotted. So that is the diagram that you see there. The very simple diagram is the system schema for the comparatively simple scenario of free fall. So the dotted of a free falling mass M. So the dotted circle around the M represents our M that's falling, like a tennis ball or something. The dotted circle represents that M. Then I followed the rules. I was like, okay, planet Earth is definitely in the situation because planet Earth is in every situation. So I drew a solid circle that says CE. CE stands for center of Earth. Or I could have written PE to stand for planet Earth, or I could write like EE to mean entire Earth, something like that. But I'm writing CE or PE or EE. To make it clear that when I say Earth, I don't mean dirt, and I don't mean like the ground. I don't mean the floor that's pushing against my feet. I mean the whole planet that's underneath my feet pulling down on me, okay? That is there. That gets a solid circle. That's definitely interacting with my tennis ball because planet Earth is always interacting somehow gravitationally with everything near it. So I draw a solid circle and I call it CE for center of Earth. Okay, and then I draw a line between the center of Earth and the mass. That line now represents the force of interaction between planet Earth and my mass. It's a pull, but you can't tell in the line whether it's a pull or a push, but it happens to be a pull. You also notice that it's a line connecting these two objects. This simple diagram is trying to connote that if we believe there's a force acting on a mass, it's got to be coming from somewhere. Part of the purpose of this diagram is to show you that you don't have lines that just start nowhere. Every line has something on both ends of it. Also, or every line segment, I should say. Also notice it is a line segment with two objects on either side. It doesn't have directionality. It's trying to remind us that if we feel that something called planet Earth is pulling on a mass, then necessarily by Newton's third law, the mass is pulling on planet Earth. And that's true. If the center of the Earth is pulling down on a brick, then a brick is pulling up on planet Earth with the exact same number of newtons of force. True story. Now that force, that interaction between these two objects, now that I have two objects and I have a line between them, it's like now I can believe there's a force on my mass. Like I've now sort of justified to myself why there is going to be a force that's going to go into my equations on at mass m, because I was able to identify some other object that is forcing it. The force itself has a name. The force of gravitational pull of acting from Earth on any given mass is called the weight of any given mass. Weight is not the same thing as mass. Mass is just an object measured in kilograms. Weight is the force of Earth gravitationally pulling on some mass. It's a force. It's measured in newtons. They're different. But so that force that comes from planet Earth is called weight. So there's my diagram. That's it. I mean, that's my system schema of an object in free fall. There's only one force acting on an object in free fall. So there's only one line in that system schema. Remember, each line represents a force, like it says up here in the top right of the sheet. It says each line in an SS is a force. Each line is a force. Now this line, and most forces are touches. This line is not a touch because this line is the gravitational force. That's an exception to the touch rule, but it's so important that it's always in every single diagram. Okay, so there's one line in this diagram. It's the one force of gravity. That's the system schema for free fall. That's it. what we would do with this is we would turn this into a free body diagram and then start doing some math. But I'm not going to do that right now. I want to give you some other examples of system schemas now to really, because this one's like almost deceptively simple. Okay, so this is it. This is the system schema for free fall. I'm going to go now to example number 2, a slightly more complicated example for drawing system schemas. Wait, hold on. We have 30 minutes. I'm going to pause for 1 sec. I mean, I'm going to pause for, if I can change it here. Can I just get, I know this is, I know this is not terribly exciting, but can I just get a electronic thumbs up or something if it's clear so far? Like, are you with me? Does this make sense? Oh, that was fast. Thank you. Abdel, Sarah, Jasmine, Tobias. Thank you. So Katya, Brianna, Kay, Osmael, Sarah. Thank you. Jose, Brian. Thank you. Katya, Jasmine, Tobias. I love this part. Okay. Thank you. Oh, and Jose. Okay. It's funny how sometimes okay. Thank you. Awesome. All right. So I'm going to assume that's you're speaking for the group. Great. And I know, awesome. Brianna, thank you. Awesome. Okay. And I know this is not as interesting as the fact that Scarlet and Violet came out 3 days ago, but just put Scarlet and Violet down for a moment. I'm putting it down too. We're just doing this. Okay. And if you don't know what I'm talking about, get Scarlet and Violet. Okay. Who knows what I'm talking? Okay. Anyway. All right. So next example, example 2, boom. Example 2. Let's imagine now that we have a fish dangling from a fishing line, from like a string, from a line that's connected to a fishing rod, okay? And let's assume that the fish has mass M and is now hanging stationary, okay? So that's my picture for it's just like a stupid picture, like there's a rod and then there's a line coming down from the rod and then there's a fish at the bottom of the line, stupid picture. But now we're going to draw a system schema and the fish is mass M. Okay, now I'm going to draw a system schema. In the system schema, it's already drawn, which takes away the suspense a little bit, but here's what I did. I drew a dotted circle around to represent M, the fish, right? So first I drew a dotted circle in the center of my page. Then here's what I did in order to make it. Then before going any further, I thought, all right, center of Earth is always in every single situation, like literally, like always in physics 203, in Newtonian, mechanical, classical physics, Earth is always there. Earth is always pulling on us. So right away, no matter with any more thinking, I draw a solid circle representing center of Earth or planet Earth, whatever, PECE. So I draw a solid, and notice I draw that solid circle wherever the heck I want. I didn't even draw it in the same place in this picture as I did in the last picture. And I did that on purpose to emphasize it doesn't matter where you draw these things. This diagram is not indicating anything about up, down, left, right. It's just trying to identify forces. So, and it's trying to force us to realize that we don't have a force acting on object number 1 unless we have object 2 somewhere in the world exerting that force. So I draw a CE, a solid circle, because I always do, because it's in every picture. And I draw a line connecting that CE to the mass of the fish. Then after I've done this, so that's what the thing is on the right. But then what I do is I say, okay, now that I've drawn planet Earth, because it's always there, whether something's in free fall or not, I always draw a planet Earth. But then I say to myself, now, is anything else going on? Well, if it was free fall, nothing else is going on. But unless, if it's not free fall, other things are going on. What else is going on? I literally say to myself, and I cannot emphasize this enough, it's so concrete once you get it. I say to myself, what else in the world is touching my object? Literally touching my object, like making physical contact with it. Like planet Earth is not making contact with it. So I put it in first before I even forget, because planet Earth is always there and it's not touching. It doesn't need to be touching for some reason in order to affect my fish. But other than planet Earth, the only things in the world that can affect my fish, my mass, are things that are touching it. So I literally now draw a solid circle for any and every object that's touching the fish. And I mean object that's directly touching the fish. So notice I draw a solid circle, like over to the left. I don't care where I draw it, I just draw somewhere. I draw a solid circle and I write in it string. I literally mean the string. There's a string that I see literally touching my fish. So I draw a solid circle for it. As opposed to the rod, Like you might think the rod is doing something. Like you might say, well, isn't there a rod touching the string? Like maybe, but we're not drawing a system schema of the string. Like the string is not the mass whose acceleration we're trying to compute here. So we always first have a dotted circle identifying the thing that we're focusing on, the mass, the M that's ultimately going to be plugged into F net equals MA, right? We have a dotted circle to represent that M. And then we're going to draw planet Earth. And then we're only going to draw every object that's literally directly touching the fish. This is so important. Otherwise, and this is, again, where people start going, like finding the more complicated the example, the more complicated people's brains get. And they start thinking, well, I know the string's sort of affecting the fish, but then the rod's affecting the string. And then what about the person's hand who's affecting the rod? And then the person's heartbeat that's affecting the person. Like you end up having Adam and Eve in your freaking picture if you're not careful, right? Or the Big Bang or something. Like the point of this is to cut things off and say, we're only going to draw everything that is directly touching the mass plus planet Earth. So I draw a solid circle for that string. And I say the string is touching the fish. So it's interacting with the fish. The string is pulling the fish. It's either pulling it or pushing it. If it's touching it, and in this case, if it's a string, I'd say it's pulling it. So I draw a line to represent that string. And now, and you might want to make a note of this, just like the pull, in fact, well, yeah, I'm going to make a running list for you when we're done with this, but there's each interaction is an interaction. It comes from a second object. The different types of interactions that tend to come up in life have different names. Like the pull that always comes up, the pull that's always exerted on everything from planet Earth, we call gravity, or even more commonly, we call weight. So the word for the gravitational pull between two objects is called weight. Similarly, the pull that gets exerted by any one-dimensional object like a string or a rope or a rod, any one-dimensional like line that that exerts a contact pull on something, we call that pull, that physical contact pull, we call it tension. It's just a word. Tension can come from a string or a nylon fishing line, or it can come from a curtain rod, with curtains overhanging windows. But whenever one dimensional physical object pulls at its ends on things, we call that tension. So there's a line connecting the string to the mass, and that is called the force of tension. Force of tension. Hold on, sorry. So now in this situation, a fish that's on a string, notice we have, and then I think to myself, is anything else touching that fish? And the answer is no. I mean, the fish is not in the water. It's just like, if the fish were in the water, maybe there'd be another thing, but this fish is just like, it's like in the process of being pulled out of the water. By the way, I say that the fish is stationary. I don't even really care. Maybe the fish is stationary. Maybe it's on its way up. Maybe it's falling down. But the point is, if it's on a line and there's nothing else touching it, then there's two forces acting on it, the line that's touching it and planet Earth. So there's two line segments in this system schema, one for each force that's acting on the fish. The ultimate purpose of the system schema is that if I look in the system schema, I see two line segments, so I know there's two forces acting on the fish. Where did I get those line segments from? One is from planet Earth because it's always there, and the other is from anything and everything touching directly the fish, which is the line. So that's my system schema. Again, please remember, I'm getting more and more complicated as I go, but remember the point of these diagrams is to simplify complicated situations. Our goal is to know what forces are acting on an object. The way we're finding out through the system schema is we're asking what objects are interacting with our first object. The answer will always be planet Earth plus everything touching our object. Okay, so there's one thing touching our object called a string. So there's one line that came into the diagram. Last thing, and then we're going to go to the third example, and we have 20 minutes. Notice now we're starting to hopefully make a little bit more concrete the kind of weird thing I said before about like the one touch, one line rule. Notice that tension line segment on the left-hand side of this picture. That tension is totally an example of the rule I'm saying here, the one touch, one line rule. Notice we have a string touching our fish, so it got one line in our picture. The one line of tension in our picture shows that one object is touching our fish. If there was a third line in our picture, that would necessarily represent another touch. I'm saying each line is a touch and each touch is a line, and tension is a perfect example of that. Gravity is an exception to that. The weight, the line called weight, was already in our picture, even though there was no touch for that, because gravity is one of the two exceptions to the one line, one touch rule. Gravity is a line without a touch, so that's an exception, but tension is a touch and it's a line, so it's totally an example of that rule. Now I'm going to draw one more picture, one more example, where I show you the other exception to that rule, but that's it for the exceptions. And then from then on, no matter how complicated the situation is, you can just follow the rule and make as complicated as a system schema as you need for as complicated a situation as you possibly could have. Here's what I mean. Here's the third example, the final system schema example. Okay, example 3. System schema, let's say we now have like a block of wood, like a block of some kind, a block of wood, or maybe like an eraser, like a whiteboard eraser or chalk. Like say you're in the lab, so you have like an eraser from the board, or you have like some block of wood or something, some slidable object, and you put it on a horizontal tabletop, like a lab table. Okay, and let's just pick some arbitrary moment where that block is on the horizontal table, and maybe just for picturing sake, maybe it's sliding along. Like it doesn't really have to be honest. It doesn't have to be sliding, but assume the tabletop is rough. And just to help ourselves picture, let's assume that someone's given the block a little push, a little like a gentle nudge, an initial velocity, and then they walked away. So they pushed the block, and now like we're taking a picture at some moment while the block is sliding of its own accord because someone just gave it an initial push. Like the person's not touching it anymore, it's just sliding along the table. And if you're thinking like, okay, won't it eventually stop? Isn't it probably like slowing down or something on the table? Won't it eventually stop? Yeah, you're probably right. Like it probably is slowing down right now, and it probably will eventually stop. And that's fine. All of these situations are like one point in space, one point in time that I'm focusing on. So we walk into the lab, we see some eraser or some block that happens to be sliding along a horizontal lab tabletop, and we're capturing one instant and one location of its motion, and we're going to ask, what are the forces acting on this object now? And we're going to in order so that we could like do the math of F net equals ma. So we're going to draw a system schema of this one object now. So what do we do? Oh, I've kind of jumped the gun and already. It's kind of bad that I've already drawn the picture, but okay. But let's go slow. Like, bear with me. Don't you jump. Well, I mean, do whatever you need to do, I guess. But so first I have a dotted circle. I drew a dotted circle around the M. The M is the mass of this block of wood or this eraser or whatever that's on the table, right? So I drew so it's my object of concern. It's the M that is ultimately going to be plugged into F net equals ma. So I draw this dotted circle around the M. Okay. Then I'm going to try to enumerate all of the forces acting on it. So first thing I do, as always, is I remember planet Earth is interacting with this eraser. And I literally remember that. Like there's no way to see that because planet Earth isn't touching it, but I just know that planet Earth is always interacting with everything. It's always pulling on everything. In other words, even if this eraser, just like the fish, even if the eraser is not in free fall, let me back up. Remember, free fall means that the only thing interacting with you is Earth. Earth is always interacting with you, though. If you're not free falling, it's because other things are pushing you up or pulling you up while Earth continues to pull you down. But Earth is always pulling you down, even if other things are also pulling you in order to counteract the effect of Earth. But Earth is always there. So, and I know I keep saying that, but I have to keep saying it because there's no other evidence for that fact. Right? If something's not in free fall, it's easy to forget that Earth is always there. Put another way I'm saying in English is any object that has mass and is living on Earth automatically has weight. its weight might not be affecting it deeply at that moment. It might be but all objects that have mass have weight. So I draw a solid circle representing the center of Earth. That's the first thing I do in every system schema. It's always there. And I draw a line connecting that solid circle to my dotted circle of mass. And that line is called the force of gravity, or in other words, weight. Okay, so down at the bottom, so I have that one thing that was in every diagram so far. Notice again, I'm drawing it in a different place each time. I don't care where I draw the center of Earth, but it's just somewhere, as long as it gets connected to my mass by a solid line, there it is. Okay, so that's force number one. Then I say to myself, I say, okay, I'm following the rule. Now I'm going to draw. Now I need to know all the other forces that are acting on this object. And as you might already see, there's going to start being more and more forces in these situations. So how do I know what forces are acting on my object? I ask myself to name any and every other object in the world that is touching my object. It's that freaking, it's so concrete that like no one ever does this. It's so concrete that everybody assumes it's going to be harder and they get themselves confused. I'm literally saying, how do you know what forces are acting on an object? The answer is planet Earth is number one, and then anything and everything that's touching your object, literally, physically, directly making contact with your object, that gets a solid circle in your system schema. So I say to myself, the tabletop is touching my mass. The tabletop is like literally in physical contact with my eraser. So I draw a solid circle for tabletop or lab table, whatever it is, okay? Again, the tabletop itself might be on legs. I'm not then saying that the legs are part of my picture too, or the tabletop might be being held up by some person. I mean, that'd be weird, but that could be happening. But I'm not drawing that person. I'm literally only drawing whatever is in direct physical contact with my mass. So I draw tabletop and I give it a solid circle, okay? So that's a touch. I'm following the touch. Now, I'm going to clearly connect the tabletop with the dotted line with, I'm going to connect the tabletop circle with my dotted mass circle. I'm going to connect them with a line segment. But here's where the other exception comes into play. And right now, I know there's words already in the picture. Don't let them throw you. It's almost disappointing that the words are already there. Don't worry about the words for a minute. Just hear me out. Earth was one exception to the one touch, one line rule, in that Earth gets a line in the picture, even though it's not touching, right? That's exception number one. The other exception is anytime two surfaces are pushing against each other, which we have here, like we have a tabletop surface pushing on the surface of this block. Now, I'm not saying it's throwing it away. I'm just saying it's pushing on it. Like they're touching each other, and they're not pulling each other. They're not magnets. They're pushing. They're like supporting each other. Anytime you have two surfaces, and by surface, I mean like two-dimensional, like plane, like area, like not a line, not a rope, and not a hand pulling or something, not a hook. But if you have surfaces, two-dimensional areas that are pushing against each other, particularly, especially if they're rough surfaces, which in reality, they always are. I mean, surfaces in the real world are always at least a little bit rough. So if you have two rough surfaces pushing on each other, they're definitely touching. They're definitely touching. They're definitely going to get a line in the system schema, definitely. But in fact, it turns out when two rough surfaces are pushing on each other, we give them two lines in the system schema. Okay, this is the other exception. For a moment, just hear me, and then I'll try to explain it, or explain why. But right now, I'm explaining the how. Saying gravity gets a line even though there's no touch, and surfaces pushing, they are a touch, but they get two lines. Anything else in your picture, anything else, for example, the fishing line was, the fishing rope, the fishing string was a touch, and it got one line in our picture. Any kind of pull, any hook, hands, anything that ever happens to anything in any of these situations, any kind of touch that you ever see gets one line in the system schema, and any line that you ever see in the system schema represents a touch. The two exceptions are that the gravitational weight line doesn't represent a touch because gravity somehow acts without touching. And we only believe that it does because we see it happening all the time. And the other exception is when two surfaces are pushing together, they get two lines in the system schema. Now, why is this? And again, I know that on the page, I'm telling you the names of those two lines, and I will. I mean, we've got 9 minutes left. I'm going to explain those names, but please don't let them they're very, very confusing names. They're very distracting. They make most people feel like they understand something, but they actually like lead to me. So don't worry about those words for a moment. I just want you to hear why there's two lines. Like, don't think, oh, there's two lines because one represents the normal and one represents friction. Like, no, like, I don't know what normal and friction are. Like, just it happens that the words are there. Why do we have these two words? Why do we have two lines? Because in the real world, when two surfaces push on each other, in the real world, surfaces are always at least somewhat rough. Even really smooth surfaces are somewhat microscopically rough. Like, no surface in the real world is perfectly smooth. So any normal surface, like a tabletop, like a lab table, and an eraser, they're both rough surfaces. If you were to zoom in, like with a microscope, and look at those surfaces, you would see all these bumps and ridges. Maybe if you zoomed in enough, you would see that those are like electrons and electron clouds or something, but there'd be like ups and downs, ridges. So when two surfaces in the real world push against each other, like my two hands are right now, in the real world, when two surfaces push against each other, really, there's a bunch of nooks and crannies, or a bunch of like teeth, or a bunch of like mountains and valleys microscopically that are interlocking with each other. So the more I press, it's like pressing two combs against each other. The teeth of the combs get like interlocked. So when the more I push my two hands together, the harder, the more I feel resistance. The more I push up and down like this, the more I'm going to feel resistance that way, horizontally. The more I press my two hands together, the harder they are to rub or slide along each other because they're rough. When rough surfaces press against each other, they also become hard to rub or slide along each other. So every one of these in life comes immediately with one of these. So when surfaces push against each other, they immediately act, whenever two surfaces touch in this way, when two surfaces push, they definitely represent a force, but I'm saying they actually end up representing two forces, one along this axis and one along this axis. Now I have 7 minutes left. What do I mean by the two axes? I don't necessarily mean a horizontal and a vertical, because the two surfaces could touch anyway. I mean, I could be my two hands like this. Thank you. Or they could be like this, or they could be on an angle. So what I'm really trying to say is when two surfaces press against each other, the way in which they press against each other, so now you can look at these words, the way the two surfaces press against each other, sorry, let me back up and say one thing. When two surfaces press against each other, think of the two surfaces as like two slices of bread in a bologna sandwich. I don't know if anybody ever eats bologna anymore. I don't even know if bologna exists anymore, but like a turkey sandwich, two slices of bread in a, but no one eats meat, a lettuce sandwich, whatever. Two slices of bread are making a lettuce sandwich. The lettuce in between them, I'm going to call from now on the plane of contact. Like when two surfaces, remember, surfaces are two-dimensional regions of space. They are planes, like geometric, like Euclidean planes, right? They're not lines, they're not dots, they're not spheres, they're planes, right? Or at least the surfaces are planes. So when you picture two surfaces pressing against each other, imagine that plane that they're slamming against. The plane in between them, the lettuce in between the two pieces of bread, that's called the plane of contact, the plane that they're both making contact with. It could be up and down, it could be side to side, it could be at an angle, but that plane of contact, when they press against that plane of contact, when they press, the way in which they press along an axis that is perpendicular to the plane, like here's the plane, an axis like pointing perpendicular to it, we call normal. In math, and this is so confusing, please bear with me. 5 minutes, I'm not saying you're not, but like tune into this because people get this is like causes so much hassle in physics. The word normal in physics and math means perpendicular. That's literally what it means. Like literally perpendicular. It does not mean regular. It does not mean average. It does not mean passable in society. Like I don't mean normal like that. And I definitely don't mean typical or regular or common. Like in other words, there's a lot of problems in physics that don't have a normal force. It's not that the normal force means a force that normally arises in problems. It means the force of contact between two surfaces that is perpendicular to the plane of contact. Whenever two surfaces press against each other, they exert a force known as normal, which literally just means the against force, the push against the plane of contact. But what I'm arguing now is whenever that happens in the real world, whenever two forces exert a perpendicular push against each other, a push perpendicular to the plane of contact, whenever they push normally to each other, then because they are rigid, they get interlocked, they become, a resistance comes into play along the other axis, the axis that is parallel to the plane of contact. When two pieces of bread slam against a piece of lettuce, they also create a force along the lettuce that makes it hard for the bread to slide smoothly along the lettuce. That component of push, the component of push that is parallel to the plane of contact, is what is called friction. Okay, this whole phenomenon together is really the frictional phenomenon. But I'm saying from now on, just like whenever Earth pulls on me without touching, we call that a gravitational pull, or we call it weight, and it gets a line in the system schema. It's a force, even though there's no touching. Similarly, when two surfaces touch each other in a pushy way, when two surfaces push against each other, they generate two forces automatically, one in this axis and one along this axis. The one along this axis we call the normal force, the normal component of surface pushing, and the force along this axis, the push parallel to the plane of contact, we call friction. Friction is just that. It's the rubbing or sliding along a plane of contact that comes about when two rough surfaces push against a plane of contact. That you never can have a friction force without a normal force. And as long as your objects are rough, you'll never have a normal force without a friction force. I mean, you could have a normal without a friction if the objects are like perfectly smooth. But okay, they go hand in hand. So whenever we have two surfaces pushing against each other, we automatically put two lines in the picture. We label one as normal, one as friction. If this object right now, we have 2 minutes, I'm just saying, if this object right now were also being pulled by a fishing rod, which could pop, or if someone also had, say someone were dragging this block along the table with a string, totally plausible, right? Say this object weren't just flying, it wasn't just like sliding by itself. Say you were pulling it along the table. Then I'd put one more solid circle in the picture. I'd have a solid circle for string. I would connect that with one line to the mass, and I'd write tension. And so there'd be a total of 4 forces in that picture. In fact, I really should do that right here, but we got 1.5 minutes, so I won't. Just note, at the end of the day, I'm saying every line in a system schema is a force acting on the mass depicted in the dotted circle of the system schema. Every one line segment in a system schema represents a force that we are then going to turn into an arrow in a free body diagram that we're then going to break up into components in a vector component diagram. And then we are going to take magnitudes and directions and plug them in to the left side of F net equals MA in order to compute A, right? That's the process here. I mean, we're ending today in 45 seconds, but where we are right now is the way you construct a system schema is you draw a solid circle for every single object touching your mass, plus you draw one solid circle for planet Earth, and you draw lines connecting your solid circles to your mass by following the one touch, one line rule, always noting the 2 exceptions, that planet Earth will get a line even though there's no touch, and every surface pushing will get 2 lines for its touch. Other than that, everything else gets 1 line for each touch. And at the end of the day, the purpose of the whole thing is that the number of lines you have in your system schema is exactly the number of forces that you're ultimately going to plug in to the left side of Newton's second law of motion. The purpose of this is to identify and enumerate the forces that we use to calculate acceleration. That's the deal. And that's class. I'm going to hang for a second if there's any questions or concerns or anything, but you've been have a good day. And thank you again for last Wednesday. Very touching. I really appreciate it. And we're done, but I'll here. I'm turning off the recording. Thank you guys. Thank you very much. And thank you for your patience. Have a great day. Have a great day. See you soon. Thank you. I totally appreciate it. Stopping the recording. Have a good day. Thank you guys. Seriously. And I'm turning off the recording, but I appreciate it.